we're winding up this unit, this topic. We're going to finish it off today. Your test is going to be, what I say, I think Thursday. Today you're going to be getting a take-home quiz. Today you might notice Lesson 5 has no homework attached to it. Your homework today is also going to be working on the ultimate review. Tomorrow we'll mark the take-home quiz. What are some questions you might see on the test? On the multiple choice, it'll be some conceptual stuff, and I'll even give you one more blatant one. You know the gravitational equation, big G, big M, little m over r squared? I'll probably give you the gravitational force, the mass of one object, the radius, and say find the mass of the other object. Get the little m by itself. Or I'll give you both masses, get the little r by itself. Or instead of gravitational force, I might use gravitational field. Remember, we used this equation to find the mass of the Earth. I might have you, find the mass of a mystery planet or something like that. Those would be kind of conceptual or fairly trivial in that they're not multi-step, multiple choicey questions. But what are you going to see on the written section? You're definitely going to see orbit. Gravity is what's pulling me in a circle. Probably the one that involves the cube root, and then one of the other ones. I don't know which one yet. You're definitely going to see how much work to lift something in orbit. Sorry, I said that wrong. To lift something into outer space, but not put it in orbit. And you'll definitely see how much work to put something in orbit, which is not just change in potential, but change in potential plus change in kinetic. What else might you see? The reason I did asteroid impacts is this gives you an idea of a conservation of energy, GG, type of question that I might ask. Now here, we just found we initially found the final kinetic energy, and then we found the final speed. That would be fair game, asking you to find the impact speed. Or it would be fair game asking you maybe to get R initial by itself. From what height was it dropped? Again, I wouldn't get R initial by itself. I would get everything. So if R initial is hidden in here, I would get everything to that side, turn it into one number, and only then would I get the R by itself. But there's also going to be some black hole stuff. So let's talk about black holes. Oh. So black holes are pretty cool. We talked last day about the first ever image of a black hole, and we realized it was showing us stuff in such a way that we were seeing actually part of it was the back of the black hole because the light had been bent so much by the mass of the black hole. It was really quite interesting. Alex, you with me? Pardon me? Yeah. Suppose an 18,000 kilogram spaceship is orbiting a black. Okay. The fact that it's in orbit, if I need to, I can say gravity is what's pulling me in a circle. At an orbital radius of 8.8 times 10 to the 9th meters, the black hole has a mass of 6.8 times 10 to the 32. Alex, what's part A asking me to find? I'm going to ask you somewhere on the written to find a gravitational field strength. And here is my fear, and this is what I'm going to say, please don't do. Someone's going to go, oh, he's asking me to, don't write this down. He's asking me to find gravitational force. And part of the problem is gravitational field and gravitational force both start with a G and an F. So you'll have to know which is which. Did I say find the gravitational force? Don't be giving me an answer in newtons. What's gravitational field? Alex, its symbol is little g. And I did give you a formula for little g on your formula sheet. Can you read it to me, please? Thank you for getting your formula sheet out. What does that mean? If you take the universal gravitation equation, which is big G, big M, little m over r squared. I think on your formula sheet I wrote it as m1, m2, but it's still the same idea. Oh, got another latecomer coming in. And you divide that by m. What I'm really saying is you can cancel out the little m. In other words, little g is big G, big M over r squared. Alex, what's big G? Yeah, the universal gravitational constant everywhere in the universe. Big M, black hole. Don't accidentally use the mass of the Earth. It's going to be 6.8 times 10 to the 32. All divided by radius, and that is a radius, not an altitude. 8.8 times 10 to the 9th. Don't forget the squared. What do you get? Sarah, what'd you get? Sorry, can you say it louder, please? 585 point, so 586, is that right, folks, or not? 586 units. You can either say newtons per kilogram. That pops right out of the actual equation, Alex, on your sheet, because it is newtons on the top, force on the top and mass on the bottom. Last year we called this meters per second squared. We treated it like an acceleration, but the reason objects on the Earth accelerate at 9.8 meters per second squared is because the gravitational field is pulling on them with 9.8 newtons on every kilogram of mass. Okay. Does that alarm us? Well, it's a black hole. I think we're expecting it near a black hole to be big. Would this be fatal to those on board the spaceship? What word did I underline? When you're in orbit, you are in two words that start with the letter F. Free fall. When you're in free fall, do you feel the effect of gravity upon you? So, if somehow we managed to get them into orbit, maybe using Star Trek technology, and beamed them in, they'd be okay as long as they were in orbit. Where they'd start to notice it would be if they tried to accelerate their way out or tried to accelerate their way in, then they would start to feel the gravitational field. Although you could probably very, 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 very gradually figure out a way to a workaround. But I'm going to say this, depends. While in orbit, they wouldn't feel G, but getting there or leaving would be problematic. And this goes back to the question that I opened up this class with about, does the sun deflect things in free fall? No, because we're in free fall around the sun. Yeah. Yep. Okay. I like part C, I like part C, I like part C. Part C is a nice question. Cohen, what's part C wanting me to find? Okay, I'm going to rederive the escape velocity equation just to jog your memory. Some of you may have chosen to memorize it. I deliberately did not put it on the yellow sheet. No, you can't add it. What was the escape velocity equation? It started out with conservation of energy, G. And it asked how much energy did we need to reach the edge of the universe, and to do so perfectly that right when we reached the edge of the universe, we also came to a stop. Out at the edge of the universe at infinity, how much potential energy did we have? Why? Because we defined it that way. We said we need to put zero energy somewhere. Putting it on the surface of the Earth would be very planet-centric. We're going to move it to edge of the universe. If we do this so perfectly that we come to a stop, how much kinetic energy will we have? And so this is why we had this strange situation where we said for escape velocity, you're actually saying you want no extra energy, but that's because the potential energy is going to be negative, defined because relative to 0 at infinity. The kinetic energy is going to be positive. We got this, a half mv initial squared plus negative big G, big M, little m over R final. That equaled 0. We then plussed this over to the other side, and that gave us a half little m v squared equals positive big G, big M, little m over R. And I wrote R final. I should have written R initial. Sorry, folks. R initial. We noticed that it didn't matter what the mass of the spaceship was, they would still have the same escape velocity. It just depends on how big the gravity field of the planet is. And then we got the V by itself. And what did we notice? We noticed that escape velocity, should be called escape speed, was equal to 2 big G, big M over R. It was inside the square root, it was 2 times V orb. Okay. What was M? 6.8 times 10 to the 32. What was R? 8.8 times 10 to the 9th. Not an R squared in this one. I forgot the 2. I do that every time for some dumb reason. Thank you. I did that last time too, I think. Forget the 2. So it's going to be 2 times 6.6. I got 3210635, but I did that really quick. I might be wrong. Yeah? So 3.21 times 10 to the 1, 2, 3, 4, 5, 6. Well, let's just suppose that Lily and Zaina are astronauts and they are orbiting this black hole. And Lily's feeling fairly adventurous. She decides she's going to put her spacesuit on and she's going to cliff jump into the black hole. She's going to leave the spaceship, and let's decide you're going to go feet first and you're going to head right for the black hole. So in real life, you would have had to cancel out your orbital velocity. You might remember, I don't know if you were here, we asked what's harder, hitting the sun or hitting Pluto? Hitting the sun, because you have to cancel out your orbital velocity. Otherwise, you'll end up in orbit around it. So let's suppose you did that. What would it be like to fall into a black hole? Well, as you got closer and closer and closer, you would reach a point, Lily, where the gravity field on your feet was stronger than the gravity field on your head. Now, that's true on the Earth. It is absolutely true that gravity is tugging on my feet slightly stronger than on my head, but it's minuscule. I can't even detect it. I bet you if I tried to calculate it, my calculator would tell me the answer was 0. I need to find a long number calculator online that could do it for me. But here, as you got closer to the black hole, because the black hole's curve of the gravity field is so much steeper, it changes much faster. You would reach a point where it felt like your feet were being tugged away from you a little bit, almost like you were stretching in the morning. And at first it would feel pretty good. We all liked, stretch. But very quickly it would become the medieval torturer's rack from hell. The difference in gravity field between your feet and your head would become bigger than the molecular bonds that hold you together, and you would bifurcate, probably somewhere around your belly button. And each of those pieces, as they continued to fall, would bifurcate again, would bifurcate again, would bifurcate again. They would split in half, split in half, split in half, until eventually you would become a series of tiny pieces, probably just molecules by this point. But not only that, space-time itself is being so dramatically warped and bent by the gravity field of the black hole that your molecules would be being compressed from all sides, like toothpaste being extruded through a toothpaste tube. And you would end up eventually in this very, very thin stream of subatomic particles falling into the black hole. And we have a name for that process. Does anybody know the name that we call falling into a black hole? That's called spaghettification. There's your word of the day. Spaghettification is what we call it, when your body gets squeezed from when the molecules get squeezed from all sides and also get pulled into chunks. You can kind of imagine like a subatomic spaghetti noodle, except nothing would be connected. They would all be just individual particles. Okay. You weren't here. Were you here at the very beginning of class? Somehow when people walked in, I started talking about all of us are dying and the world is ending. So we're just continuing on with our, the universe is out to get you theme. What I really like is example 4. I like example 4. Suppose, a black hole has a mass of 7.2 times 10 to the 31. Suppose a spaceship is 9.6 times 10 to the 9th meters from the center of the black hole. What's the gravitational field strength? Try this one on your own. I'll do it up here. See if you can find gravitational field strength. Remember, we're not finding gravitational force. Make sure you can see how I did hide the equation on your formula sheet. Is that right? Okay. 52.1. About 5 Gs. Survivable, but it wouldn't be pleasant. B asks, what's the escape velocity required to leave the black hole? We just did the equation, so I'm going to jump into it. I think escape velocity. Don't forget the 2, Mr. Dewick. Thank you. 2 big G, big M over R. Wait. Look what I have typed on my calculator. I have big G, big M over R squared. You know what? I think if I just backspace delete the squared and stick a 2 times in front, and then square root that, I don't have to retype the whole thing. I'm going to do it that way. Jan, you're following along and typing along, right? I didn't need to remind you to do that? No. Never. Two, three, four. Double check me, that's what I got. I might be wrong. Phone, is that what you got as well? Okay. Ten to the 6 is what? About 1 million meters per second. Okay. C. Is that all right? C. At what radius from the center of the black hole does the event horizon begin? So the event horizon, that's the specific location where the gravity field has become strong enough that escape velocity is faster than light. So what we're going to do, Alice, is we're going to start out with our escape velocity equation. And we're going to get the R by itself, because that's where the event horizon is going to begin. And for V, we're going to let V equal the speed of light. So to get the R by itself, I think the first thing that I would do is I would square both sides. When I square both sides on the right-hand side, Nick, the squared and the square root just cancel each other out. And I end up with this. V squared equals 2 big G, big M over R. Zaina, what's this question asking me to find? At what? Let's get the r by itself. Where is the r right now? Multiply it to the top and divide the v squared over at the same time. I'll get this. R equals 2 big G big M over v squared. R is going to be, I can go back 2 lines. First of all, I'll write it out. 2 big G. What was M, Mr. Dewick? It was 7.2 times 10 to the 31. And then V is going to be the speed of light. I gave that to you if you forget. It is on your formula sheet. I think it's in the chart where I give you near the top of the page a bunch of constants in the same chart that has big G. I think at the bottom of that chart it should say speed of light is 3 times 10 to the 8th, right? It's my way of saying make sure you know where it is. So 3 times 10 to the 8th squared. (7.32 times 10 to the 31, 3 times 10 to the 8th squared). You get 106,720? Or if I make that into kilometers, about 107 kilometers wide. I'll go 1.07 times 10 to the 5th meters. So, Keegan, how did this star become a black hole? The way it would have worked is, for a long time, a few billion years probably, the star would have been burning fuel inside. We call that fusion. And that fusion exerts an outward pressure from the inside of the star. At the same time, the star's mass would have been exerting an inward pressure, gravity. And that tug of war, it's not that you're not pulling, but that pushing against each other, that equilibrium, Sarah, lasts for a few billion years, but the star is constantly manufacturing heavier and heavier elements at its core, and eventually it reaches the point where the outward pressure of fusion is smaller than the inward pressure of gravity, and the star begins to collapse. If you were there, it would take a while, but if you were there watching, you would see the star not lose its mass, Nick, but it would be getting smaller and smaller, denser and denser and denser. My mom says I'm dense, Keegan. She means something else. Getting denser and denser. And suddenly, when the radius became a little more than 106 kilometers, the star that you were seeing would suddenly vanish because light could no longer escape from it. Now, there would have been some weird light effects going on well before that. There probably would have been what we call an accretion disk, as objects that are orbiting the star speed up faster and faster and faster. And so that was what we talked about last day when we talked about that image of the black hole. But that is when it would become a quote-unquote black hole. So, example 5. Suppose the sun began to collapse. Maintaining its mass, Lena, I'm killing us again, I know, I saw the eye roll. Maintaining its mass but decreasing its radius. At what radius will it become a black hole? We call this the Schwartz radius, named after the physicist who first wrote a paper on it. It's the same thing as the event horizon. So we're going to start off with, again, starting out with escape velocity. We're again going to get the r by itself, square both sides. We get v squared equals 2 big G big M over r. We would again multiply the r to the top left and divide the v squared over. And again, we'll let v equal the speed of light. So we're going to get this. 2 big G. What's the math of the sun? I know it's 1.98, but I can't remember the rest. 10 to the 30th? In case you're wondering, Quinn, the sun's mass is not quite large enough for this to occur. You might notice all of the black hole masses I've been giving you haven't been 10 to the 30th. They've been 10 to the 32, 33. The sun is just ever so slightly too small for this to occur. It's about 10 to 100 to 1,000 times too small. Keegan, what'd you get? Oh, I didn't need to remind you to go to your calculator, did I? Oh, that'd be silly if I had to do that. I'm being lazy because I have 2 times 6.67. I just need to change this. 1.98. Scientific notation button 30 divided by 3 scientific notation button 8 squared. And this is also a time, if you're not getting the same answers as me, this is probably where you want to figure out how your calculator works. I got 2,934. Basically, about 3 kilometers. About the distance from here to the McDonald's. Okay. That's roughly 3 kilometers, I think. So the sun would have to get pretty small. 2,935 meters. Put your pencils down, look up. How big can black holes get? That's a good question. Turns out, pretty big. You ready? Because this is actually going to be pretty mind-blowing. In fact, we calculated this one, 3 kilometers. Here's a nearby black hole, fairly small. So that one has the mass of what? 3 to 4 of our suns. Let's kick it up a notch. The size of Mars. About 1,000 suns. It's a meh black hole. So the Phoenix cluster, I don't know if you can see, that's the size of our solar. So it's a fairly large black hole. How many masses does it have? 20 billion of our suns. There are a fair number of those out there. So we have a black hole, we believe, at the center of our Milky Way galaxy called Sagittarius A star, and it's got about a 4 million solar mass black hole. So black holes can get pretty big.